created by MindSticks Foundation Trust.
Hello and welcome, students. Today we're diving into a really foundational chapter in our mathematics syllabus. We are going to systematically unpack what quadratic equations actually are, look at their standard form, figure out how to correctly spot them, understand what the roots of an equation mean, and finally learn how to find those tricky unknown values. Let's jump right in.
Starting off with Section 1. What exactly are quadratic equations? Let's do a quick recap of what we learned last year and see how it actually applies to a real-world problem today.
Now, I want you to just recall your previous syllabus regarding polynomials, right? We basically categorize them by their degree. Take a look at the linear polynomials first. When the degree, meaning the highest index, is just 1, like in the expression 5x plus 9, well, that's a linear polynomial. But contrast that with the quadratic polynomial. When the highest degree is exactly 2, for example, x squared plus 3x minus 5, it magically becomes quadratic. So the number 2 is really the hero here.
Okay, let's look at a practical application. Because, we don't just study these equations to pass exams. They are literally tools for solving spatial challenges in our daily lives. Consider this scenario. Sanket purchased a rectangular plot having an area of 200 square meters. The length of his plot is 10 meters more than its breadth. So, how do we convert this simple English sentence into a solid mathematical equation to find the actual dimensions? Let's solve this puzzle together.
Let's just walk through the logical steps very patiently. Step 1. We don't actually know the breadth, right? So let the breadth of the plot be x meters. Moving to step 2, the problem clearly tells us the length is 10 meters more, so the length naturally becomes x plus 10 meters. Step 3, we all know the formula for the area of a rectangle. It's length multiplied by breadth. Therefore, x multiplied by x plus 10 gives us the total area, which is 200. Now for the final step, let's open up those brackets. X into x gives us x squared, x into 10 gives us 10x, and if we bring that 200 over to the left side, we get x squared plus 10x minus 200 equals 0. And there you'd have it. That right there is our very first quadratic equation. Moving on to Section 2, the standard form. Now that we've seen exactly how these equations naturally emerge from real-life problems, let's formalize our understanding by looking at the standard mathematical rule. Please pay very close attention to this definition, as it's absolutely crucial. The standard or general form of a quadratic equation is ax squared plus bx plus c equals 0. Here, the letters a, b, and c represent real numbers, but there is one very strict condition you must remember. The value of a absolutely cannot be 0. Why is that? Well, think about it. If a becomes 0, the x squared term completely vanishes, and poof, it is no longer a quadratic equation at all. The x squared term is quite literally the heart of the whole equation.
All right, Section 3, Spotting Quadratic Equations. Let's test our observation skills now and see if we can easily spot the true quadratic equations from a lineup.
To confidently identify a quadratic equation, you just need to check for 2 strict textbook rules. First, the equation must involve only one single variable. It should be entirely in x, or entirely in y, or m, but no mixing. Second, the maximum index, or the highest power of that variable, has to be exactly 2. All indices must be positive whole numbers, but the absolute maximum must be 2. Nothing more, nothing less.
Let's practice this with a couple of quick examples. Look at our first equation, x squared minus 4 equals 0. We really need to write this in the general form of ax squared plus bx plus c equals 0. But notice, there's no middle x term here. So, we simply write it as x squared plus 0x minus 4 equals 0. Comparing this to our standard form, we can easily see that a is 1, b is 0, and c is minus 4. Simple, right? Now observe the second equation, y squared equals 2y minus 7. Wait, this is not properly arranged. We must bring all the terms over to the left side first. It then becomes y squared minus 2y plus 7 equals 0. Now, who can tell what the values are? Yep, a is 1, b is minus 2, and c is 7. This rearranging step is a real game changer, so don't forget it.
Let's move forward to Section 4, Roots of an Equation. We've learned how to write the equation down, but what does the final answer actually look like? What even is a root?
The textbook defines a root very clearly. A root, which you might also hear called a solution, is a specific value of the variable that perfectly satisfies the equation. But what does satisfies the equation actually mean? Well, it just means if you take that specific number and put it exactly where the variable x is, the entire left-hand side will calculate out to be exactly 0, perfectly matching the right-hand side. It balances the scale perfectly.
Whenever you're asked in an exam to check if a given number is a root, you really must follow these 4 methodical steps. Step 1. Clearly write down the polynomial equation. Step 2. Simply substitute the given number in place of x. Step 3. Carefully perform your mathematical operations. Square the numbers, multiply, add, and subtract. Finally, step 4. Check your final result. If it comes out to exactly 0, then yes, it's a root. If it is literally any other number, it's not a root.
Let's compare 2 quick examples side by side using the polynomial x squared plus 5x minus 6. First, let's substitute x equals minus 6. Minus 6 squared is 36. 5 multiplied by minus 6 gives us minus 30. And then we just carry down the minus 6. So 36 minus 30 minus 6 equals 0. Because it equals exactly 0, minus 6 is a true solution. Fantastic. Now let's try substituting x equals 2. We get 2 squared, which is 4, plus 5 into 2, which is 10, minus 6. So 4 plus 10 is 14, minus 6 equals 8. Since 8 is obviously not equal to 0, we can confidently say that 2 is not a solution. It really is that simple.
Finally, we reach our last section, Section 5, Finding the Unknown Value. In exams, questions are sometimes flipped around. Let's learn how to work backwards to find an unknown letter when the root is actually already given to us by the examiner.
Let's carefully solve this little activity together. The question asks, if x equals 5 is a root of the equation kx squared minus 14x minus 5 equals 0, find the value of k. Because we already know x equals 5 is a root, we can directly substitute 5 right into the equation. Let's put x equal to 5. We get k multiplied by 5 squared minus 14 multiplied by 5 minus 5 equals 0. Now, 5 squared is 25, so we have 25k. 14 multiplied by 5 is 70. So 25k minus 70 minus 5 equals 0. This simplifies neatly down to 25k minus 75 equals 0. If we just move that 75 over to the right side, we get 25k equals 75. Dividing 75 by 25, we finally find that k equals 3. By simply following the basic rules of substitution, we algebraically hit the nail on the head and solved for the missing constant k.
As we wrap up this explainer, I want to draw your attention to a quick summary box to really consolidate today's key takeaways. First, make sure to memorize the general form, ax squared plus bx plus c equals 0, where a, b, and c are real numbers and, most importantly, a is not 0. Second, always remember that the specific values of the variable which perfectly balance and satisfy the equation are called its solutions or roots.
Before we conclude our lesson today, I want to leave you with a bit of a provocative thought just to test your fundamental understanding. Look back at the standard form, ax squared plus bx plus c equals 0. If a accidentally became 0, what type of equation would it instantly transform into and why? Just think about the degree of the polynomial that would be left behind. Keep pondering on this logic, as it's going to perfectly set up our next class. Keep practicing your sums, students, and thank you so much for joining this explainer.